Hello everybody, welcome to another stream. How are we all doing? How's it going? Only having fun, welcome, how are you? Right, so today's an exciting day, we get to, oh, okay, right, I might have to, right, I'm gonna have to try and get my son back to sleep, he's just woken up again, and I thought he would go back to sleep again, but he is. He just started moaning, which means he won't go back. So, be right back. I might be back in like 10 more minutes, maybe a bit longer. So, yeah, we'll start then. Apologies. Right, welcome back everyone. Sorry about that. Oh crap, where to leave? Oh, I see it, good. Well, left the monitor in the room. Right, is there, is down. The boy is down, the stream can start. How's it going? Hey there, Wajilla. Hey there, Stone Monkey Mark. Well, I missed the stream, sorry, I really want to watch this one. Do you do the STF for the ellipse or correct or mass approximations? I do, I'll be doing just a Rayverse ellipsoid using IQ's ray intersection. He's got one for an ellipsoid. It's quite alright actually, because it's basically just an extension of the sphere one. Or I might end up using the sphere one, but the normal might be wrong. Anyway, there's one for an ellipsoid in here. But yeah, there's also a VOD channel as well, where it will be up on. But yeah, it's literally just a few dot products and then a square root. So yeah, to get the hit position along the ray. So that's not bad. Let me put this over. Right, so today we're going to be beginning rewriting the rendering of this game, because there we go, that's what we want. The current one's got a bunch of glitches and it's not performant enough, and it's not the one we're going to be going with in the end, so I want to sort of just, it's also missing a feature or two that I was going to add. So I was just thinking, why don't we just go ahead and get the rewrite out of the way and get started on that today. So currently the existing one, if I take a screenshot and open up in the screenshot viewer, you know, it doesn't have any anti-aliasing. I've solved that problem in the past, and I want to solve it today, hopefully. I want to test out something which is implementing MSAA in software, hopefully. So because that's probably the main objective, we want to just literally get a very simple shader which just ray traces a couple of ellipsoids, and we'll use the we'll keep the PBR so as to have the cube map and image-based lighting, but we won't set up many resources to like pass data in, because there's no need to do that to test it all out. So if we find, so I'm just going to get a compute shader started up. If we find BV8, yeah, so let's just disable the BVH renderer. Just completely gets rid of a lot of stuff, or everything to do with the BVH. So where we do this one here, we're going to copy paste it and we'll rename it. So all this is doing is, from the CPU side, just launching a compute shader full screen. We'll pass in the scene texture we're going to render to, the depth texture that it needs to write out to, and that should be it. So we call it the ellipsoid, or ray tracer, let's just call it that. Or it'll eventually be tile binned, but yeah, let's just call it that. Yeah, so if we, yeah, we need to sync on those environment map resources. Right, so let's make this type. This is just a structure which holds all the push constants. That's all it is. So we'll literally just make this in the shared header file, which is shared between CPU and GPU code. It's got an output texture and a depth texture. It's also output too as well. So let's find where that. Let's go to the shaders file. Let's call my shaders in a single file for now. Don't think we'll probably need to split it out. So BBH Raytracer, if we take this guy, copy paste it. Oh, I don't know why I'm doing that, to be honest. Let's take the start of it. And I want to take this line here and use that line instead. So ellipsoid Raytracer, there we go. Cool. So we'll leave this line comment out for a second. So let's just output to a texture. So we're going to store out. Let's just store the gradient, right? Final color. Let's call it. Yeah, final color. Just keep it as that, right? So vector 4. Final color. We'll do. Float equal .x divided by graphics global scene dims. Yeah. So repeat that for the Y as well. So we get a nice red green gradient, 0 for blue and 1 for alpha. So let's try that and see what happens. So with this compute shader, we're doing 8x8 as in the group. So there's an 8x8 set of threads in the group. So on most hardware, it's 2 waves that run in lockstep in a single group. I don't think we'll be using wave intrinsics for this or any quad intrinsics. That's just something to be aware about. And then, yeah, then obviously the dispatch code is literally just saying, given the screen dimensions, right? So say if you've got a resolution of 1600 by 800, it's dividing that number by 8 and rounding it up, and then that will launch that many groups of 8x8 pixels. So that's why you need this if statement in here to say if the coordinate goes outside the bounds of the dimensions, then we're going to return early. Yeah, so this just gets the pixel coordinate basically because it's just the overall index from all the groups and the offset into the group. Cool, so if we give this a launch now, hopefully it doesn't burn the computer down. What's going on here? Oh, did I put... Oh, I need to say .x, right, and .y. Whoopsie. Cool, so we should just see a gradient on the screen. There you go, so inside the editor, where this is rendering the scene image, we're just seeing that gradient, right? My coordinate system is always the lower left is 0, 0. So yeah, that's the way I've decided to do things for this. Cool. So I guess let's just define a structure. We can always change. We'll change it later, but we'll just call it an ellipsoid strut. What I'm doing there, same the way I usually do it. Cool. So effectively, what we want to do is ray trace in. We'll start the ray trace out in view space, but then we'll turn it into world space, and then we need to define some transform which will get us back into the local space of the ellipsoid. So yeah, so we'll call this world from local, and we can then also pass in some form of material index, I guess. Do we have any materials uploaded? Material index, something like that. In future, we can worry about packing it down and actually see the increased performance by packing this data down. So let's talk about this little line here I've commented out. So if you just use the dispatch index, the issue is let's get that one out. It's going to fill it out in row major order. Yeah, so if you have, let's say you have a thread group or a dispatch group, what we're going to call it, if I can get this right. Cool, that'll be it. Oh, it's completely wrong. All right, it's a bit better. Oh well, anyway, so that's an 8x8 grid. It's not very even, but there we go. So that is a thread group. So if you just use the dispatch index, your threads are going to be ordered like this in this row major order, right? Where it just goes across the X, and when it reaches the end, it goes down. So this one here would be index 31. And this is obviously index 0. 32, 33, and so on, right? So your first wave of threads which run in lockstep will target this, and your next set of waves will target the second half. That runs independently of that top half. So what this line here does is it swizzles it takes the group index and gets you into the same place as before, but it swizzles these such that it does it in a Z order, so it's using the Morton Z curve. So your threads will be ordered like this. So the index will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so that's done a little micro Z like that, a more sort of macro Z order, right, of a group of 4, 4, 4, 4, so in that order. And then it will just keep repeating in that pattern. Basically, you think of it as like a tree of Zs. So it will grow. So why would you order it this way? Well, there's two reasons why you order it this way. One, well, there's a few then. One, pixel shaders do it that way. Yeah, pixel shaders do it that way, and then it will and that means, and the reason why they do it that way is such that in a wave, so a wave is typically 32 threads, or threads, it's just a SIMD unit 32 wide. When you have this like if you use the quad intrinsics, so the intrinsics which allow you to take one thread and pass data to the other one in a quad, and the other way around as well, obviously. These intrinsics work based on the wave indices. So they work on if your thread index within a wave whoops. So 0, 1, 2, and 3 will all be one quad, right? And this wouldn't work these wouldn't be a quad if it was laid out in this order. So by doing the Z curve order, it will now be in a quad. So the wave intrinsic or the quad intrinsics will work in compute shaders. And the second reason why you do it is because there was some AMD talk where they said if you swizzle it like this, the storing, when you store stuff and read stuff in textures, I think it was just storing, it might have been reading as well, but it's basically more optimized if within a wave it accesses for some reason in this sort of 2x2 if the quad is like in this fashion apparently. So they're the reasons why you do this. So we're just going to do it that way. Maybe we can comment out and see if it makes a difference later, but yeah. Let's leave it there just in case so we can see. So what's the first thing we want to do is probably set up the ellipsoid data, and then, well, yeah. So let's just make a couple of ellipsoids. Well, from local. Oh, whoops. I want to make an array, that's right. World from local. So let's just do a let's just do some translation for now. So we move that. Let's just keep it center, and then we'll move it like back. So yeah, be positive. So let's just move it back to about 40. Then I think we need to set up the quaternion. So we'll call it rotation. So I think it's identity like this. All right. Oh, what happened there? Cool. And this other one is, we probably want to set as the material index. Let's say that is, let's just do 0 for now. So we want to go over all of the ellipsoids probably. So anyway, one in there for now. And so this is where we need to actually start with this ray tracing. We need to declare a ray. Right, so here's a previous one. Right, so here's one sort of made earlier. It passes in the field of view and the dimensions of the render target that we're rendering to, and the coordinate that we're trying to render for that texture. So all this function does is where we get the drawings out again. So imagine if you have your camera like so. There'll be some sort of like plane here where the texture is, and all it does, let me get it, should have done the line tool to be honest. Bit like that. All it does is, say if you're rendering this pixel here, it figures out from this location how across the 3 dimensions, you know, what's the ray direction. that I'm firing out based on the field of view, right? Because if you have a like a thinner field of view, your texture is actually going to start a bit much higher. I think that's how it works. Yeah, and the wider the field of view is, the closer it will be to the camera position. So, yeah. I could go in and explain all of that, but there's plenty of resources online about it. But I can just quickly jump to the code. So is that in... Might be in core shared. Yes. So just add 0.5 to it so that the center of... If you got a... So that you're in the middle of the pixel, right? Then it subtracts away half of the dimensions of the texture away, such that you're now 0, 0 is in the center of the screen. And then it does this sort of, gets the height of the texture, divides it by tan of field of view divided by 2, and that gets you the Z component. And then you just normalize the vector where the X and Y go in XY. Yeah. So there's some stuff to do with that trig, basically. You know, this is makes like a triangle, and you're getting sort of this distance, and that distance is also like the height of the texture. But you can do your own little research in on it. Yeah. Anyway, it's just too much going to today. So, ray direction. Now with the ray direction for the pixel we're trying to render, the ray origin in view space is just 0, 0. So this guy here, where it's starting out, is in 0, 0, 0. And now we want to move that into world space such that, so rather than moving moving all the objects back into view space, we can also just move the ray around, and that's the way that the all the intersection code is actually going to work. So world from view, I've got one of these matrices already in the yes, here's some code I made earlier. Don't normalize it, it's a bad idea. Yeah, it's a bad idea. Right. So yeah, we just pass in ray direction view space, and we put it as transform, get the world space one out. We just apply the rotation and scale, and then for the position we do the same, but we apply the translation as well with the multiply. So the next thing we need to do is actually see if we have that ray versus ellipsoid. We already do, it's here. So yeah, so right. So this is already copied over from Inigo Quilez. It's just this with this normalized one as well. So we need to transform into the local space of the ellipsoid itself, and the ray will be in the local space of the ellipsoid object. So rather than, so you're doing the, so here's your ellipsoid. This will be the origin, and then when you have this sort of like ray this ray origin here, it's going to look like that instead when you're doing the sort of when it's in this ray versus ellipsoid code. It's going to be relative from here, so it's like drawing a vector from there to there basically, and it's rotated around it as well. So if this ellipsoid has rotation, it's actually going to be rotating the whole view. Cool. So yeah, it's just doing a ray versus ellipsoid. It fails, it returns -1 in t. So it doesn't handle if you're inside maybe. Yeah, perhaps we need to. Yeah, I don't know. We need to probably test it out. That is for sure. Cool. So we should be able to just plop that in there like that. And we'll get back some. So this is the result. So the ray origin, so we need to transform into the local space of the object. So we get ourselves the ellipsoid. We can just call it E. Ellipsoid's E index. And then, so we've got this sort of like world from local thing. So if we, we want to move everything back into local space except for the radius, because the radius is the scale. Right. So local space. Yeah, we want to do it without the. So the transform instead is just got individual components. Let's go to the core. Right. So yeah, this is just a special matrix that just has things separated out. So this applies the rotation, but not the scale. That's what I want. And then a position. Yeah, but I want the opposite of that. I wonder. Maybe we need to define another function. So we need to go from world space to local space. But I've already got one, the inverse. Yeah. So I want to do that, and then I want to take away the position before. Yeah, I want to make another one. Let's make another function. We'll call it a UP maybe. So UP would mean to do like a unit. Keep it. Just don't scale it, but it'll flip it if need be. But it'll still do the translation. That's what I want. Yeah, let's do that. So this one will do the. Yeah. So what's great about this type of matrix as well is you can do the inverse with that. without inverting the whole thing. But, you know, it might be better just to invert the whole thing first. Maybe. Yeah, we could just inverse it. So transform local from world is equal to the inverse of e dot world from local. I guess we'll do that. So we're going to multiply this vector and not scale it, so just be a u. Local from world, and we're taking the ray direction from world space, moving it to the local space of the object, and we're doing the same thing for the ray origin, but we're doing it with we don't want to scale it. So that's great, cool. All right. I didn't put any scale actually. And have I got a bit of time in the global structure? I think I've got time in there. Yeah, time in seconds, amazing. So I can just make it grow and shrink. So if we do something like along the x, we'll say sine based on time in seconds multiplied by 10, and then we'll keep it. You want to do times 0.5 plus 0.5 to make it 0 to 1 instead of -1 to 1. Maybe we'll times it by 20 and keep the others 10. Cool. Maybe 10 is a bit big. Let's probably do 4. Right, so there's our ellipsoid. Whoops. So he's passing the ray origin in local space and the ray direction in local space. And the radius is literally just going to be e world from local. Ooh. Yeah, scale. That's it. That's why I didn't want to do the scaling, because this reverse ellipsoid depends on this radius in here. Anyway, right. So if we look at t, if that is greater than 0, I guess I need to solve for if we're inside the ellipsoid. We'll sort that out in a bit. Yeah, so in this case, so what we're trying to do is we're trying to find probably the closest hit, I guess, but let's just say if we hit one of them, then we'll break. So if we've hit, we set final color to something. So how do we know if we've hit? Should we just have a Boolean for now? Or a t value, really? Closest hit t. So what space will this want to be in? Well, yeah, that's the thing, right? So we want to include a depth value. So really what we want is actually a hit position. So you want the hit position in, well, Yeah, you want that hit position in world space. That's what you actually want. And then well, yeah, let's just do hit the closest hit T. This would be in view space. So it's making infinity. Now we want to also render like the cube map if we miss. So we want to say if isinf closest hit depth, there is the cube map that we can put in there. So that's in the ray tracer above, isn't it? Yes, it's this code here. Oh, I need it in world space. Of course. Whoops. So we want it in world space. Right, so if it's infinity means the color wouldn't have been set. So we're going to sample the cube map in the ray direction. And yeah. It's an sRGB texture. It needs to be made into HDR. Oh, that's right. And it blends the pixels front to back. So I guess it would have. I don't know why it needs to do that. Because there's nothing on the screen there yet. Cool. So let's take a look at the other code up above just a second. So this is where if we got a hit, we're going to do the shading with the material. So this is the PBR setup basically. So we got this shading structure where we pass in a view direction, surface hit position, surface normal. These are all calculated internally, but they're just passed around, and it just makes it easier to pass a single strut around. I think we passed a couple of struts, but yeah. Then I unpack the material from the global material, seeing that will come from a buffer somewhere, and we'll have multiple materials. Then we calculate the shading. Calculate the surface color, passing the shading in the material. So I already need a function that just does this for me. Yeah. So we've got to fill in these things. So we need a hit position and a normal. Shouldn't be too bad. Right. So the way you fill these in is they come from the ray code that I've already got. So, okay, I've already got it, but these are in local space of the object, so you need to go back the other way. The way you go back the other way is use the. So this is a position, so it needs to use the position 1. Whoops, that should be saying transform 3D. Transform 3D. Then we need to pass in the. Oh, why are these using that graphics global thing? All right. So world. Wait a minute. Yeah, why are any of these using it? It's not. It's not global. It's coming from a local declared. Right here. And this one is going to be e dot or from local. And we're transforming this R hit position. Then we do the same thing but for the normal. But the normal is not a position, so it needs to just do the rotation. Yeah. That's right. And then we'll break. We've got to put the hit T in. So the way you probably calculate hit T is you've got to take the world space position and just take the difference and do a length. So it's like a length with a subtraction between the closest hit in world space, right, not local space, or in world space, from the ray origin in world space. Wait a minute. We're not applying any scale though. So if we're not applying any scale and just rotating and translating, then that means the hit T is going to be the same. So we don't need to do any of that. That's great. No need to translate or to recalculate. Since the since the ray direction is not scaled. That's correct. Well, would that even be true? Because this scales it here, basically, right? So well, yeah, if you scale it, you can make a line very long. If you scale it. Divided by A. Right, I guess it turned... Yeah, I think that's true. Yeah. Cool. So this code is looking like we can probably run it soon. We just want to double check what we have, because if I crash the GPU, my whole PC dies and it'll be sad. Right, so from the top, we get the pixel coordinate right, and if we're outside the bounds of the texture, we return. We've got our array of ellipsoids, but just one at the moment. It's 40 back. Maybe we can make it 50. Maybe that'll be too far, I don't know. We're not right now to the depth texture. We could do that. Where's the depth texture? Nope. So the depth texture. Closest hit T. I guess I could call it depth, right? That's another thing we could do. But anyway, back up here. So got our ellipsoid. It's got the translation, rotation, and scale, and it animates the x-axis. We can get it to rotate in a bit. Ray direction based on the screen dims, that seems alright. V space obviously starts at 0, 0. Nice. Maybe we'll put them the other way around. Just the way I like to read it. So multiplying a point here, so ray origin right from V space to world space, and then multiplying a vector from V space to world space. Final color is initialized to black, but not to worry because we do set it regardless. So we could, well, let's just leave it like that for now. Set the closest hit T to infinity, and well, let's get rid of it. This one needs to be set to infinity. These don't have to be set. So closest hit position in world space, go over all of the ellipsoids, fish out the array. Inverse the world from local transform to make it a local from world transform. Use the local from world transform to calculate the local space, ray origin, and ray direction in the local space of the ellipsoid. So the ellipsoid will be at 0, 0. Pass those into the rayverse ellipsoid and this scale from the world from local transform. And if it's positive, it means we've got a... Wait a minute. Yeah, if it's positive, we've got a hit. Then... yeah, we need to sort this out in another... Right. Yeah, so we're doing the position, so it's we don't want to scale this, it's just the rotation and the position. Well, from local, that's right. And it's just the rotation. Nice. Sweet. If it's infinity, yep. Sample the environment map. Display the environment map. These are incorrect. View direction. Wait. View direction and what? This is world space normalize. Yeah, duh. Yep. The global material that we have right now, and voila. That looks like it, right? So let's give this a run and see what happens. If the stream dies, I'll be right back, but it's just my AMD card. For some reason the drivers do that. I need to buy a new one. Right, someone spelt something wrong. Oh, is that duplicate def? Oh, let's put a P there. Right, what is this one? Ooh. Used the wrong, I'm gonna use a comma, isn't it? Right, that needs to be a floating point. I could have made it, to be honest. Right, infinity, I got my own little infinity. Cool. Right, let's go. So I see something moving here. We're seeing like this bit bizarre. It's like gaps in the pixels. Right, we're seeing an ellipsoid there. It's looking alright. Although there's like I don't know what's going on. So if we open up the texture viewer, we can actually see what's going on by looking at the scene. So it seems we're only rendering, I don't know what we're rendering, it's hard to tell. But at most, I think it's a 4:2. Something is pretty buggered up. Like, so I've applied some post-processing effect or something. It looks like some sort of like old art or something. Cool. I don't know what I did. Could it be my swizzle thing? Don't think it is, because we've done this before. It is my swizzle thing. It's not respecting the what's this really dark? Like, what is this? Oh, this is sRGB. Yeah, we didn't do the sRGB conversion. So since we run from a computer shader, you don't get the auto magic sRGB conversion. So what you need to do is you need to do it yourself manually. You know, we've already got some functions for that. So it's like linear to sRGB fast. So so that's the reason why it looks so dark like that. is it's not, yeah, there you go. I need to not open up the editor as often, but there you go. So there's our ellipsoid. We're able to get close to it. There we go. Hey. And it just stretches out. So let's look at why that swizzle thing's not working. I don't know what's going on. I thought this worked. Like, what did I do it for? What have I done it for? I've done it for the color picker. Oh, I've got to do 64 in the local group. It'll still be 8x8 though. Right. Yeah, nice blob. It's a good looking blob. It's a PBR blob. I want to go to the editor quickly and just tell it no. You know, that it's not visible, because by default it's visible and it just gets in the way when I'm doing editor programming for the next little bit. So why is it off center? That's a good question. Well, I think that's because in the graphics code, when we initialize the view from, well, in the game code, well, in the, I think it's in the game code, the default camera is moved. Where do I set the game camera from? I thought it was set in the, oh, game update. I actually have a game file now, I remember that. But yeah, the base camera, yeah, it's actually moved along the X and the Z. Right, let's move it up a bit. Let's put it flat like that, let's do it. So I've got a really high field of view right now, just so I can sort of test to make sure my things don't fall apart with a higher field of view. But yeah, it's that one. So there we go, here's our test object. So we'll hopefully make these jagged edges go away. But we're going to make another test object behind it, which is probably going to be smaller. See, I wonder, should that... Yeah, it should... Hey, Pinkerton. Yeah, I'm doing good, man. I'm doing good. Yeah, just been, you know, working, spending time with the family, and yeah, it's been good. You know, I just got to the boy back home, and he was in a laughy mood, which means typically he's on the brink of being tired and crying. But I managed to like tickle him and get a good video of him, which was fun. And then he wouldn't go to sleep. Like an hour later, he wouldn't go to sleep. So I had to spend time running him around. Physical was down. It's not rotating, it's stretching. Boom. The field of view is just so damn high, probably. It's just difficult to tell. What the music was. Okay, so I guess shall we get another smaller ellipsoid in front of it, maybe? So we say, like, if it increases by about 2, we can also give it a base of 2. Or let's give it a base of 4. And then let's get rid of this code here. Neat. So let's make another ellipsoid, which is behind it. We'll put it such that they're in order, because this is the way it's going to work. they're going to be sorted by Z order. Well, yes, this is going to fall apart and break if I move the camera, but that's okay. Let's move a bit further back. And let's make this one not move. And let's make it be 10 in width along the X. So hopefully that works. Hopefully. Alright, somebody messed up his brackets. Somebody's me. Right, should have two ellipses now. One is static at the back, and the other one grows and shrinks. And I cannot see the second one. Right, is that because this one is too big and in the way? No. Oh, because the for loop doesn't go above 1. So I don't have a way to do size of array in shader code because it involves pointers using usually, and my shader compiler doesn't support pointers. Yeah, so we'll just set up, maybe we'll make this one a little bit smaller. Let's make it sort of like 2, 2. Change that to 1 and 2. Strong the sphere 1998 vibes. Not sure what that is. Hey there, Cranston, how you doing? Yeah, so now we're seeing that the horrible anti-aliased edges, sorry, horrible non-anti-aliased edges, and we're seeing them here as well. So now I'm going to try the experimental thing, which is a software MSAA implementation, where we're going to implement MSAA in software and try and anti-alias the edges. Now, yeah. Yeah. So I'm just going to take a. I'm going to be busy with terminal colors, like true productive Linux user, right? Do you go full true color with that, or did you settle on something more old school like 16 colors? Yeah, I'm just gonna take a quick break and get another drink. But when we get back, we'll talk about like why we're going the MSAA route and what problems it solves and how we're going to approach it. So yeah, right. BRB. Alright, welcome back everyone. How you doing? Our eyes only see up to 10 million colors. We need an upgrade. Yeah, apparently chickens see more colors, I think. I think that's right. What I've heard. Maybe we should all have chicken eyes or something. I know. Oh no, yeah, 16 colors, right. Consistent throughout X11. Nice. Cool. That sounds pretty neat. Sounds like you live in the terminal. Right, maybe we can move these things a little bit closer. Well, maybe it doesn't really matter so much, but I guess let's do 40 and 90. So we actually can check a little bit of performance. Where's the here it is. We enable this, and it'll turn the profile mode to individual shaders rather than the full frame. Full frame, it just gives you the obviously the full frame, but we can insert more timestamps into the command buffer and get ourselves all the shaders. So we see here. What have I done to my profiler? Oh crap. I deleted the names. Alright, let me fix that quick. Crap. Where's the name come from again? There's a way. HCC shader info shader name. Yes. But didn't I used to sort of like has to be a static string. Yeah, it doesn't matter. Yeah, so it is the same thing for indirect as well. Right, I'll fix it. Oh, that'd be good. Audio. So, yeah, we're looking about 0.2 ms at the moment. There we go. So, what we're looking at doing, apparently you specify term info entries in bare stack machine like language. Huh. Wait, where'd you specify this term info entry thing? I've not seen that before. Right, so in the past, the way I've done anti-aliasing is I've made this Rayverse Ellipsoid or Rayverse sphere, I had it as a sphere. I made this more expensive by like, I think it was tracing how close the ray was to the edge of the sphere. And I don't know if we could do it for the ellipsoid, but so I had the sphere and I had a ray, and I was like, well, and then here's like the pixel, and we're saying like, well, because this ray is like half a pixel width away from the edge, or you could do one which goes inside, or it's half a pixel width inside. Inside but away, but close to the edge by half a pixel width. Then you sort of like make this pixel transparent, and you carry on the ray and merge that color, or blend that color with a hit from behind. That's what I did in the past, but then that means you've got to do like transparency, and I just want to do like an opaque hit. I want to have a shader which just does hits the closest thing and then renders that. So I want to move away from that and go to something a little bit different. The alternatives are you use something like you do it in post, which is you do like a post anti-aliasing step, which is what games do these days, but it's got temporal, it's like TAA and all these different upscalers as well. It's all temporal, and I'm not really a fan of the temporal stuff. So I'd like to try and not use it. So we're going to try doing MSAA. So we can go over what MSAA is. It stands for multi-sampled anti-aliasing. So you take multiple samples in a single pixel and you merge them, merge the result at the end. So essentially it's kind of similar to, or we might say this is, you could say it's an optimization of super sampled anti-aliasing. And we can go over what those are. Yeah, so the idea, I guess we can just say if you got a pixel, and within a pixel you've got a 2x2 set of pixels, but there's this pixel will be the final pixel. And the reason why we're doing it in software is because I want, like, the biggest problem with Vulkan is there is a there's two reasons why we're doing it in software. The problem with Vulkan is it's a very complicated API, and the more features you use from Vulkan, the more you sort of tie yourself into doing more complicated things. And MSAA, my multi-sample, is another example of that. Then also the other thing is I want to try and not write out to a texture and do it all in a single shader pass. So this should hopefully help with the memory bandwidth issue. We're writing less memory out. Yeah, so maybe if it's using the hardware one, you could probably, it has its own way of doing it probably. It's but yeah, the reason why I want to do it all in one pass and not sort of output some high resolution and then just and then do a second pass where I make it into a smaller texture and downsample it, is because I want to not write out basically 4 times the amount of pixels, right? 2 times in each direction, and that will hopefully be a lot more performant this way. So I guess what is the difference between like super sample and anti-aliasing? I guess maybe they're the same thing. Because I know there's a trick in MSAA. The super sampled AA, is it just literally a downsample? Yeah, because of the memory bandwidth. We're going to get around that problem by not writing it out. Or write out the final pixel. Okay. Yeah, because I know that they're different, so I imagine. Sounds a bit weird. Yeah, so renders game a higher resolution and scales it down. Yeah, that's as you would expect. So super sampled anti-aliasing is just rendering it at higher resolution basically. Whereas multi-sampled is, I forgot now, what is this? Get out. Term info is the thing that takes commands like make foreground red and then translate. Yeah. Right. Yeah, it's always fun doing that stuff. I remember doing my own terminal applications and following that sort of VT100 standard. It was quite fun. Then there's the extended Xterm stuff, and then yeah, it's great. And then it even supports mouse these days, so you can do mouse in terminal. It depends on how massive the object is. Gravity bends the line. Right, and use a single sample within primitives. That's interesting. Yeah, that's right. Well, yeah. So that's what I was gonna go over. There's that optimize. That's true, isn't it? Well, it only takes single samples, from my understanding, right? Is it always takes single samples, but it just blends. Yeah. So with MSAA, from my understanding of the way it works, is that you have a pixel, and it will just. Oh well, it will have to do. No, we'll have to do multiple samples in the edges, wouldn't it? Yeah, so right. Principle of about breaking the bank in terms of performance. Yeah, in order to keep the benefit of supersample without breaking the bank, we can observe that aliasing of triangle visibility function, aka geometric aliasing, only occurs at the edges of the rasterized triangles. If we hopped into time machine drive about 2001, we observed that the pixel shading mostly consists of texture fetches and doesn't suffer from aliasing due to bitmaps. Right. The coverage and inclusion tests are formed. Conceptually, it has 4 sample slots per pixel, but only populates more than one on primitive edges. The result is then there's a weighted average on the samples, weighted one. Right. Subpixel morphological anti-aliasing. Yeah, but isn't that still like TAA, isn't it? I looked into it, I forgot. But it's still some sort of post. Oh no, it was a mixture of FXAA, wasn't it? And something else. Yeah, it's a post solution. And it does edge detection. Yeah, I remember now. So it only calls the pixel shader once, doesn't it? That's my understanding. It only calls the pixel shader once for every single object, but it will place it in the different sample slots depending on how the triangle overlaps the sample slots. Three grayscale textures and then blending. I'm not sure. Yeah, I've not heard that before. At least for me, the conceptual model doesn't make it clear how MSAA saves memory bandwidth. I guess part of the quality of implementation, secret source. Maybe there's some heuristic where you can sort of, yeah, I don't know. You know, at most there'll be this many edges or something like that, and you could allocate space for it, and it's, I don't know. Calls a pixel shader. Well, there's probably a lot of special hardware actually, isn't it? Calls the pixel shader once, pixels that are entirely in the primitive. On edges. Right, okay. So on edges it's more than once. That would make sense. Yeah. Because otherwise you wouldn't get the shading. The shading wouldn't be correct. Yeah. Right. Gotcha. So, yeah, so basically, with like MSAA, if you have your 4 sample points, I think they're slightly a bit different. But if you have your triangle, one triangle that goes like that, and then you have another triangle that goes like this. Very terrible triangle. So this is technically 1 pixel, but it's got a what is it? MSAA times 2 or something like that, or something like that. Where it splits into a 2 by 2. Yeah, I guess I'll run the pixel shader for this one, and this one. Or I guess it's called the fragment shader at that point, isn't it? It's coloring this fragment in. And then it'll call it for this one, and then they will get, in a later step, you resolve it by merging these pixels, and you sort of get, you know, you get it's mostly this triangle's color with this yeah, with this triangle's one slightly in it as well. So I'm thinking what we can probably do is we could try and not do the extra samples, I think, all together and see how it looks. So maybe what we can do instead is, so it might not be correct. It might be a bit weird around the edges, but we'll see how it looks. If not, we've got to figure out how do we, if we're near the edge. But the thinking is, if we say, if instead we have this will always be, or maybe, Yeah, we'll still shoot the rays. We'll shoot the rays through these pixels and do our, this time with ellipsoids. Right, you have an ellipsoid that goes like this. And you have another ellipsoid which goes like that. The ray will still go through these. And get a hit through the, and hit these ellipsoids. But when it tries to do the shading, what it's going to do instead is always shade it from the center. So I guess we'll have another direction where it's going to put the, I guess you have to recalculate the normal maybe. Or maybe it won't matter that much. You could probably pick the lowest numbered sample, which one, and use that normal or something, and shade it once. So it'll only do the material shading once, and it should be okay. And then, yeah, we won't be paying the cost for shading too much, basically. Yeah, so let's give that approach a go, and then if it doesn't look right, we can always try something else. And that way it should be... Yeah, and then we'll resolve it before we write the pixel out, and then just write the pixel out. Write the final pixel out. So we want a way to... So I wanted to do this... by literally just putting a for loop in the shader. So you could probably do it with like quad intrinsics or wave intrinsics, but then you'd have to write a specialized shader for each type of MSAA you want. And it's probably not, yeah, it's not very scalable. And you'd also have to somehow pass the samples around over the wave intrinsics as well, and it's be weird. So we'll be doing that way. Hey there, Helios. Welcome. So this video about AA, let's take a gander. Maybe I can watch it later. Oh, it's an article. I read his video. Analytical anti-aliasing, get rid of jagged edges is an art form. Right. So this is doing it in post, isn't it? Oh, this is cool. It's got graphics for graphics blog. And it's got video. This is great. I might give us a read later, actually. Thank you so much. Yeah, I can't read it now because I'm one, slow at reading, and two, other stuff to do, but I'll definitely look at that later. Thank you. I'll post it on the Discord as well. Someone suggested... Okay. There we go. Yeah, there's Discord if you guys want to come out and hang out in the meantime as well. That is that. Is it in the depth test the colors are blended instead of overlaid? No, you do a manual resolve later on. So in MSAA, proper MSAA, there is a resolve command. So there's like VK command resolve image, and that will resolve the MSAA stuff. Correction to my previous. I think the sample weights are All other than 0 and 1 only populated or not populated. Oh, or only either 0 or 1. Okay, yeah, I thought I read it that way actually, but maybe I misread. If more advanced weighting is needed, alpha to coverage, etc., it's done by populating more than one sample slot from a single fragment shader invocation output. So weights that come from units. Oh, so they do it the way I was thinking initially. But only if you got alpha to coverage on. Right. I see. Thank you so much for that. It's a great clear up. Yeah, so it's essentially it's an optimized SSAA. MSAA is. It just doesn't do as much work. Oh, Artie, no problem. Yeah, it's cool. I love reading stuff. I like your project. It's great. What's going on here lately? Well, doing the classic thing of an indie game developer. I'm rewriting the renderer again. So we're doing the renderer again, or just the ellipsoid bit. Ellipsoid renderer. I'm going back to something else because it's more performant and it's less buggy and more simple. But yeah, so that's what we're currently working on. But yeah, how's your project going? So we're just trying to do our hand-rolled MSAA, basically. So I think the idea is that we need to be able to get. So say if we had, right, let's just say there's a sort of MSAA mode. So you got it in a 1 mode. You can't have it in a 0 mode. Doesn't make any sense. And there's a yeah, they do it in powers of 2, isn't it? They do like a sample thing, but yeah, 1 is off. I guess it's like a yeah. How do they do it in Vulkan? It's like a sample count thing, isn't it? 1, 2. Oh, they have a 2 sample mode, right? On a 2-bit. Okay, I see. Right, that's the way I wanted to do it anyway. That's good. So yeah, we'll call that mode to enable 2. So then you want to have your sort of like I guess we'll call it dim to be right. So the way we got to do it is yeah, we want to not take the yeah, we've still got to do the Rayverse ellipsoid test, isn't it? So we have this sort of like coordinate here. Actually, we don't have the coordinate there. Somebody. Oh no, we do. It's offset by 0.5, which means we need to offset this coordinate here by a quarter of a pixel. And then relaunch the ray out. So you need different ray directions depending on yeah, it's going to add up, isn't it? Maybe we will need different compute shaders. There might be a way you could Right, interesting. Okay, fair play. It's great. Yeah, always end up rerunning the render. That's classic. Well, I rerun render a couple of months. Well, having any rerun render a couple of months ago, the open world support is going really well, and first planning meeting with the first attached voice actor for the project earlier today. Oh, cool! I didn't realize you was getting voice actor in there. Nice. Cool. Awesome. Yeah, I like how you've gone with the route of procedural generation. It sounds, yeah, because yeah, it really gives the game a lot of content, doesn't it? People can just keep coming back and keep playing it. That's why I like procedural generation. But yeah, I'm considering doing procedural generation for this project and maybe not at the same time because, yeah, but it's cool. Awesome. Rayverse. No, ray direction for pixel, right. So, yeah, like, the problem is you can't simply just nudge the ray direction by a core of pixel, because with the field of view, the further it is to the edge of the screen, the more. Is that right? I guess we could test that with quad intrinsics. We could tell whether or not the step between 2 pixels. Yeah, let's compare it. Let's get the derivative. What ddx? Yeah, what kind of game would be Ryan? Yeah, it'd be an RPG. Do like a top-down RPG game. Yeah, should be fun. It won't just be me making it. I want to sort of get the rendering looking really nice, and then go and get some editors in here so we can actually make content. And then I want to be able to probably build some kind of like, get the basic sort of, probably get the basic parts of the gameplay in and systems, and then probably start trying to figure out how do I take that to the end and figure out how I achieve that. But yeah, so I think that would be over the next couple of years, is that load of work. But yeah. So I swap with the X. I can figure out if my theory is true. So let's say if your pixel is equal to 0, or is equal to the global scene dims divided by 2. So I'm checking if the so at 0, 0 and at the center of the screen on the X, I'm seeing if the difference between the two rays are much bigger. we put on the Y to be in the center of the screen. And if they are consistently, if the difference between the rays in a 2x2 are the same, then it means we can just use a bit of maths to do this every single time we go to the next object. But if not, we've got to store it. We've got to pre-calculate them and store them maybe. Yeah. So I want to see, trying to avoid caching them into some locals. So DDA, where was it? Quad. That's it. So I'm swapping with a neighboring quad. The problem is you've got to do it for... Yeah, we'll do it outside. Right. So in a 2x2, swap and then get... Always swapping the ray direction dot x. Cool. So we take the difference. And then I want to print that out. So the coordinate would be u coord.x, and then the difference is diff. Every floating point. Good. Right, so let's see how that looks. Ah, shoot, what did I do? Awesome, thank you. Crap. Some do brackets. All right. Okay, so we're seeing the two values printed out. So, yeah, the theory is correct, right? So, the pixel in the middle of the screen is the far left, and its neighboring pixel. You take the difference between those two ray directions. We use the quad intrinsics to swap the value, right? The difference is 0.0000, right, 391, whereas the one in the middle of the screen, right, the difference is bigger apparently. I thought that... Right. Should we do another couple just to see? Bizarre. Let's do another one at 100. It should be somewhere in between those two. Yeah, it's bigger than that one. Nice. Right. Theory has been proven, so we're going to have to store a local set of values, I think, for each of the samples, which means that... Wait, or we could recalculate the ray direction. Yeah, it'd be expensive, I reckon. So we'll just store these in here. So you'd have your subsample. So I think we're going to need a separate shader now for each. MSAA basically. So I think we'll do something like this. And we'll probably have to put it in a separate file and include it multiple times for different amounts of multi-sampled. Hey Voodoo, welcome sir, how are you doing? I didn't know much about, but I wonder, why software MSA? Why not do it on the GPU? No, I'm doing it on the GPU. It's still happening on the GPU, but I'm doing it within a compute shader manually. It's a bit like how I'm doing a software ray tracer. I'm doing it in a compute shader manually rather than doing using the hardware. And I'm resolving it within the same compute shader, but I'm just doing it manually. So just ham rolling it basically. Yeah. So essentially you're gonna have, you probably want to say if MSAA dim equal 1. We'll do the old way. And then if not, we'll the new way. So the new way is gonna have all your samples in here. So because you've got MSAA dim, and you probably want to have MSAA samples count will be the square of this. So dim is across a single dimension. But yeah. Samples count is all of the individual sample points. Then we need to initialize this thing. So in order to do that, we will need to probably do a for loop. Multi-dimensional for loop. So essentially this code here where it does the ray versus ellipsoid is essentially our rasterization step, where we're going to rasterize and figure out which pixels hit what ellipsoid first. And then afterwards we'll do our shading on however many times we need to do shading. And then we'll do our resolve step after that. So this will just be a ray direction y times MSAA dim plus x, so that just flattens it out. And we're going to store in here. So we need the dims. So we probably want to have, I'm not sure how much we want this, I want to keep it around. But yeah, this would be the MSAA scene dims. So that'll just be this. Multiplied by, or scaled along each dimension by the MSAA dim. Cool. So all this is going to do is, right, so this coordinate here, this would be the MSAA coordinate. It will be a, yeah, I could cast it later. Cool. So what I want to do is scale it by the MSAA dim. then add, C30 times 2. I want to add a XY to it. So you could probably do, yeah, that should do it. So we're scaling it by 2, and then we're adding, adding 0 or 1 basically in this case. And we'll recalculate our ray directions like that. So we'll have our if-def for, so this is the rasterization step thing, you know. Yeah, I don't know how much we should keep this one going. Let's just make it full MSAA style. Well, maybe what you can do is call it MSAA like that. Then you can still keep it like this. So you'll have this sort of like for loop. If it's not equal to 1, you'll put a for loop in there. And then at the end, if it's not equal to 1, you obviously just close the for loop. Then you just need a ray direction. So there's a ray direction in world space. I think you only ever need it in world space, really. Is that true? Yeah. So actually, I did this one a little wrong. We want to be transforming the world space one instead. Yeah, I think we might have to do it that way. Right, so this will just be the ray direction view space. Then this multiply goes here. And these would be world space directions. Nice. Right, so the next step would be to multi-sample so to basically ray trace in this sort of super sampled fashion in this 2x2. So rather than having just one pixel, it's split into a 2x2 at this point. So do that for loop. So there's a ray direction. So this will not be defined if we got this pass on. So what we'll need to do inside here is declare it based on that. So something like this. Ray direction, world space, something like that. Okay, nice. Right, so what this is doing is saying if one of these samples hit, then we're going to break, which is incredibly bad. So So I think the way it needs to work is we need to ray trace against. So we're going over every single ellipsoid first, and then within that ellipsoid, we're checking all the samples to see if it hits the ellipsoid, right? We're just doing a simple for loop. So we get to reuse. We'll get to reuse the this aspect of it, but that aspect we won't. So all we're planning on doing is saying, did I hit? That's all we want to know, I think. Did I hit, and which sample hit and what object did it hit? So that would mean we probably want to store an array of So we probably want to store maybe an array of ellipsoid index. Based on the sample that you've hit. And then with that, we can later on go over all of these and then if I wonder. You probably want to search over this ellipsoid. Yeah. And then figure out how many times it's been hit or something. Yeah. So I reckon you can store the ellipsoid MSAA object indices. So it's got at most this many samples. Then you want to store the weight. So you could probably optimize this a bit by packing it down maybe, but because if you have a lot of samples, this will use a lot of registers, which is quite problematic. So you want to be careful of that. So then we'll probably just store, hey, this is how many objects that we've, unique objects. Yeah, you could probably pack that down or something. So I reckon when we get a hit, instead what we do is we search over this array look and see if we've already got the object in here. If we have, we up the weight. If we haven't, we add it on, then up the weight. So yeah, let's just write that code. Yeah. So call like a sample index thing, something like that. And we'll just say if MSAA sample object indices s index is equal to the e index, so e meaning the ellipsoid, right? then we will store then we'll just up. Well, it would say we've found it. And then break. So hopefully, right, my expectation is you might be like, well, we're doing a for loop in here. Well, at most it's going to be filled up with this many samples, but most of the time in a pixel, you're going to be having just one object in here anyway. Maybe what we could do is we could cap this out to something like 4, or maybe even 2. 4 is probably the best number. And then even if you up the number of samples, you change this to something like 8, right? It won't be 16, which is, it's quite a lot of registers to take up in a shader. So like most of the time, you're gonna have like just one object in there for most of the pixels. So it's just gonna hit there and break. So it should be quite a lot of the pixels within the same wave will take the same branches and the same number of iterations typically, and unless it doesn't, which is around the edges. So it should be okay, hopefully. So if we've found it, we just want to say MSAA sample object weights, or it should be weights with an S. We simply just want to up the okay. We simply just want to up this found weight by 1. We'll keep it as a float, be alright. Then if not, we would like, so these weights are not initialized, so we're going to have to just basically set it to 1 here. Or yeah, we're going to at least have to set it, so we'll set it in here as well, and then do indices is equal to S index. Sorry, E index. Now, this can't be found index, so it has to be that weight count, and then we'll up the count by 1. So that's an insert there into that array. Now it shouldn't go over because it's equal to number of samples, but if we change that, we're going to have to make sure that we don't insert more than we can. Yeah. Cool. So now we've got the number of objects and their weights. In terms of like a closest hit, what does that mean? Well, what I'm thinking of doing is, so say if you've got this is a single pixel, but we've split into a 2x2 set of samples. I'm thinking about, so this is essentially the rasterization step. So it's not doing any shading, right? It's just figuring out what pixels hit what object. When we, but when we do the shading, it's always going to be done from this center ray, the original center ray, right? So what this means we need to do is take the closest, like I think if we literally just take the closest, whichever one of these hits the, yeah, we use this if statement, right? If it's not equal to infinity, well, yeah, if it's equal to infinity, when we find a hit, we'll encode, the closest hit T maybe. If we encode the closest hit T, We can then recalculate the closest hit position. And then we can recalculate the normal. We're going to have to redo it. Or do it manually down here, but that's okay. I'm happy with that. Yeah, so that will be... These will come down here. To save it being a branch, you could do a min. And that way, so there's no break either. You only break if you've hit, if all 4 samples have hit something. Because if not, this is just going to keep going. So we need to intelligently do that. So let's do a min between itself and the current. Cool. So yeah, we need to optimize this. So we can't just break but we have to break if all samples have been hit. We don't know. Yes, we have to retire this. So I guess we can do a bit set. So we should be able to condense this down at some point, but we do a bit set for MSAA. So that would just be just use 4 bits for now, or whatever. So we take that, and so we go if so we get ourselves the sample index, which is just a flattened version of the x and y. If MSAA hit bit set and one shift left sample index, then we continue. So that is going to actually make it such that the you're going to have some threads within a wave which are inactive, which is kind of bad. But yeah, hopefully it's just for 1 or 2 checks. Yeah, hopefully the next ellipsoid is it hits, basically. But yeah. Right, there's a much better way you can do this. You can remove the for loop. You can do the least set bit index. Yeah, so say if you set this to 1 shift left, that take 1, that sets all bits on. Then what you can do is do the super lovely while we have some bits, MSAA hit bit set. So you do while we have some bits, and then you can get the sample index by doing what is my least significant bit that's set. It's just an intrinsic I have. It's built into GPUs as well these days. So you can sort of scan for the first bit that's set as a single instruction. Right. Then we need to make sure at the end of the for loop that we do the little trick. Have I got a thing which removes the least set bit? Right. It's not in shared though. I'm moving this into shared. So it's shared between my CPU and GPU code. Hey, Captain Chica. How you doing, sir? Let's check it here. So this removes the least set bit. You just take one away from your value and AND it with itself. And voila. Yeah, this is just more descriptive if I do it this way. So we say MSAA hit bit set equals like that. Right, so now we can remove this for loop thing and just use the while loop. Way better. Right, so we don't have X and Y though, which could be a problem, but it might not be. Yeah, so now we don't have to have this for loop anymore. But there will still be the lanes which will become inactive because some threads will carry on longer than others in the while loop. But this is okay. So the least set bit index. And then get the ray direction in world space. Transform it into local space. The object. Do the ray versus ellipsoid check. Now I wonder how much of this you could yeah, I think the compiler will probably optimize some of this. Probably just that square, to be honest, because all this is dependent on the ray direction, which changes per. Yeah, there's not much code that could be optimized from there. Okay, so you've got a hit. Go over all those objects. Sample object. If we've found the index. Cool. Is not equal to U32 max. Then add one to the weight. If not, insert a new object. Nice. Closest hit. Now we no longer have to do a break. Wait. Yeah, how are we doing it? So the only time we remove the fact it's not really a hit anymore. So it's the not hit bit set. There we go. So we want to remove this if it's been hit, we want to remove it from the bit set. Awesome. Right, that all makes a lot of sense. Cool. Right, hopefully we can get this up and running actually. We're pretty close. So this is the rasterization step. It's a bit weird, but this is the way. This has got to be initialized to 0. If not, that will fall over and cry, and I'll cry. I had to write a HPP file for the first time in a long time. I can't remember what they used for. Oh. So, aren't they like no different? They're just a way of saying, hey, I use C++. It's a bit silly that all of C++ headers are not HPP, because syntax highlighters and editors be like, oh, this is C++, but you know, my headers are C, so it does that. Right, I'm liking this. This is good. So after this, we need to calculate the hit position. So the hit position gets calculated by moving the original ray. So we need to get the original ray again. So I need it to be redeclared. So if it's not equal to 1, we're going to calculate the original ray that goes through the middle of the actual pixel rather than in these sort of quadrants of the pixel, right? And then we're going to take our hit T and we're going to shoot it over ray direction in world space. Yeah, so we've got it in view space and then moves into world space. Then we're going to calculate the hit position in world space by taking the ray direction. Okay. All right, so it'd be multiply scale ray direction world space multiplied by the closest hit T in world space. Then we're going to add the origin, ray origin in world space. Cool. So the normal, so the thing is, right, is I calculate the normal within that sort of ray versus ellipsoid code because I had it all done it all in one, but really yeah, I need it as a separate function. We need to do it later, so this could actually probably be optimized and we can remove some of this stuff, or it gives you back the hit position and the right. So we just want to pass in the hit pos and the radius of the ellipsoid. You see, we could just pass out so R2 squared radius. So now we need the actual radius of the object, which was the closest hit. It's quite a bit to store, to be honest. So 3 registers. Wait. No. You're storing the indices, which means you can refetch it. The issue is, yeah, the closest hit normal will have to be done. Right. Right, so if nothing hit, we just sample the background. But if something hit, we've got to do the shading for as many times. So we need to make another bit set. No, do we need to make a bit set? No, I just need to go over the... Yeah, go over the number of objects that we've hit and their weights and do the shading. Over no extension. No extension? Huh? That's weird. Don't you want to recognize your files? HXX and yeah, 6HXX, right. Sounds pretty old school. Because that's what it was recognized as before, wasn't it? As HXX. Right, so we want to get the object indices and object weights. So ellipsoid index, then we need to sample. So that will be S index. Then we'd like to also fetch the weight. Right, so the first thing we need to do is calculate that normal and the hit position, then shading. So all of this stuff here, kinda. Something like that. So I guess you can call it color 3 up here. We'll instantiate it to 0, so just black. So we need to do like a weighted average basically. So we want to recalculate this normal, so we need to go into those ellipsoids with the ellipsoid index and fetch out the scale, which gets us the radius. So that will calculate a kind of correct normal. The normals will probably be off because it's doing the closest hit from here. Oh, yeah, the closest hit is probably not a good idea. We probably need a depth per sample because, but yeah, we want to do it along the ray from the center though. Yeah, which will have, right, I see. So we probably actually want to have a depth per object, per one of these. Right. Yeah, we can probably pack these down a whole lot and save some registers. Wait a minute. Yeah, the object's already been in there. Yeah. So hit T. Let's move this comment. So I think actually, right, you don't need to do the search. You don't even need to do this search. It's you just keep a boolean around. Right. That might be it. This closest hit is no longer a thing. So this is saying if you have no objects that you've hit, there's an optimization that you can do here. You don't need to do this loop to find. Well, yeah, you only need to do the loop to find. Anyway, you use it as an extra register though, but yeah. So within this, you just say has hit ellipsoid, and you just say, well, if it's hit it, you set that to true. Now, the problem, yes, you go if has hit ellipsoid, you do the search, you find it, you add the weight, and you bail. And there's an else statement where it will do this insertion instead. So since if it has hit the ellipsoid, maybe instead of being a simple boolean, this can actually be the ellipsoid, what do we call it, an S index. So by default that'd be U32 max, so it hasn't been inserted yet. And then we won't have to do the for loop search, it will just be or already be done, right? So if that is not equal to U32 max, then there's no need to do the search. We simply just increment the weight. All right, this is even better. Then we need to make sure though that this is set to the count when we insert. All right, that's a really nice optimization. Saves doing those silly searches. Nice. It's even better. Cool, so now we've got the depths in there, so we've got the depth. Right. The problem is... Right, let's just handle the MSAA code. I can't be bothered to get the other one to work yet. We can do that later. So we have all the hit objects, get the object out. Closest hit position is fine. Oh no, we've got to work out those, that's it. Yep. Right, so the depth, where's the depth? This is it. So hit depth, MSAA, sample object, depths, S index. Cool. So the hit depth will be here. And the normal, yes. Do the shading. Yes. Closest hit position and normal. Cool. Shading. Nice. Now we get the weight. And we add to the color. So add color 3 multiplied by the weight. So the weight is going to be, so for every single time the object is hit by one of the samples, the weight goes up by 1. So we multiply them all by the weight, and then we divide by the weight. That should be the weighted average. And that. Right. So we keep accumulating that weighted color, and then at the end we do the division. Inverse total weight equals total weight 1 divided by total weight. We need a total weight. Right. Plus equals, missing that. So inverse total weight, and then we multiply this by the inverse total weight. So it's just a division, just more optimized, since it's going to be multiplying 3 times. Or since it would have been dividing by 3 times. You know, 3 different components, X, Y, and Z. Cool. Then you finally get the final color, and you output the final color. So that should be the MSAA thing sorted out. So we can give it a go, see what happens. Right, so let's just double check and make sure everything's makes sense, because if not, we could mess things up. So you let's just do the build step, catch any errors. Right. Redirect was it 3.9? Alright. Oh. This one needs a recalculated one of these as well. Yeah, why is it done in the loop? Screw it. There we go. Nice. Oh. 23. Inverse total weight. Oh yeah, I gotta make that. And then we store the closest hit T in the text. Yeah, so from all the samples, what is the closest hit T? That is a good question. Right, so in this case it will be infinity. Closest hit T world space. So infinity. And then in this case it will be the min of, well, yeah. So in this case it will be the min. Where's the depth? Here. Hit depth. Nice. Right. U64? Who put U64 in there? Was that me? Just a bit set. Ah, this is only for U64, damn it. No, it cannot be shared. Right, let's go back to core quick. Core.h, put it back in there, nice. And then in the shader, I've got to use the 32 version. Cool. Right. Apparently that all compiles. Let's double check, make sure the logic all is sound. So we go over all of the so we multiply the scene dimensions by MSAA dims. We go over the Y and X axes with working out the MSAA chord by multiplying it by the current chord by 2 basically, and then adding a 0 or 1. Then we are taking the high resolution scene dimensions and that high resolution subcoordinate, right, and calculating a specific ray direction for that one. Then we are inserting it into that array of ray directions for every sample. Cool, that makes sense. Now we are we'd put in all the bits on, 1 bit for each sample to say this MSAA sample has not been hit. Final color shouldn't need to go here, it should go here instead. We've got number of objects 0, weights, depths, and indices. Hopefully we can reduce the number of variables we use in here, because this will impact performance. So we go over every object, right? This is the same. It's just the same. So if the ellipsoid has been put into this sort of list of sampled objects, we will take note of that so we don't have to search the array. We go over every single sample that's not been hit yet. We get that sample and we get its ray direction from that pre-calculated list up here. Then this array is a real bug of this. This uses a lot of registers. That's 3 registers for every sample. That's going to be quite expensive. But maybe there's ways that we could cheese it and do an incorrect, calculate it every single time based on the sample index. I think that would be better. Right, then we just transform it into the local space of the object, or the ray direction, and do the ray versus ellipsoid. If we have a sample index, if the ellipsoid has been hit by one of the samples before, add 1 to the weight. If it hasn't, this is the index for it. Then insert into the array, just to make things a little bit, oh my days, a bit shorter and easier to read. We'll do that. Put in the ellipsoid index, start the weight at 1, and put in the hit depth, and then up the count. Since we've hit, we want to remove the least set bit, which marks that we've hit this sample, so we don't need to retest the sample again for the next ellipsoid. And when all samples have been done, if all samples are done, we want to break this. We need that sort of while else thing, If that is not set, then don't traverse over the ellipsoids anymore. That will be a big savings if there's lots of ellipsoids over the same tiles or the same pixels. Right, so we calculate our ray direction again, but this time through the center of the actual pixel rather than the subpixels. If we didn't hit any objects, then we sample the cube map or the environment map. If not, we've got a total weight. Go over all the sampled objects, pick out the ellipsoid object, index, and get the hit depth. Calculate the closest hit depth overall. Recalculate the hit position, this time going down the direction of the center of the screen based on the hit depth. And calculate the normal, this time properly. Well, it's slightly incorrect, but it shall do by passing in the scale and the hit position. Yep. Do the shading. Yes. And then, do the shading, get the weight, add. Multiply the color by the weight and accumulate it in color 3. Accumulate the weight, then inverse the weight and basically divide color 3, completing the average, and then final color is color 3. Sweet. And then we basically just output it to a texture and voila. Cool. Right, so we're going to give that a go, and hopefully all works like a charm. We should have nice anti-aliased edges. Fingers crossed. I'm just going to take a quick break though, and then we'll test it out in a minute. Right. Right, here we go. Hopefully this works. Yeah, if the stream dies, I'll be right back, but it shouldn't die. We've tested, well, we just went